Hi, this video is, I think, sort of a fun application of thinking about what will happen to a charged particle that's moving in a uniform magnetic field. So you can see that I drew these arrow tips facing out at you, and they're sort of uniformly distributed through the space. So we'll say that this indicates a uniform magnetic field that is directed at you of some strength in Teslas, right? And now let's imagine, for simplicity, it's sort of easier to talk about the way a positive charge would move under the influence of this field. If I take a positive charge and I put it in this background magnetic field and I give it some initial velocity, let's say the velocity is exactly towards the right and the magnetic field is exactly out towards you from the screen. So that means that the velocity and the magnetic field are perpendicular, and what you're going to get in this uniform field is a circular trajectory. But what's interesting is this circular trajectory is just a flat plane, and the particle's going to go around uniform circular motion. But what if, instead of making the little positive charge move directly to the right, what if I gave it a little bit of motion also, say, towards you, right, out of the screen? So I'm going to do that now. So that's just a second. Let me erase this trajectory and this velocity vector, and let's imagine instead a velocity vector that is partially coming out at you, but also headed towards the right. So that velocity vector, let me draw it with some perspective. So it's coming out at you, and but also is moving towards the right. Let me draw a different perspective of this drawing, right? So let's imagine I have a field line, and it's headed, so this is the magnetic field. It's one of the field lines in the magnetic field. And there is a little positive charge that is crossing the field line, so that's a little positive charge, but its velocity is simultaneously sideways to the magnetic field, but also along the magnetic field. So if this is the velocity vector, right, you can see that there's an angle between these things, and it's not 90 degrees. So up here, it's hard to see the perspective, but there is an angle that's not 90 degrees between the direction of the magnetic field in the background and the velocity of our little positively charged particle, right? So what I want to do is show you that in this particular case, what this particle is going to do is it is going to wind around in a circle, but also head out of the page. It's going to do a motion that is helical. So what I'm trying to indicate is the trajectory of our little positive particle is going to be something like this. It's going to follow a helix. Helical motion is a combination of uniform circular motion combined with a drift. And the drift is going to happen along the magnetic field line, and the uniform circular motion is going to happen transverse to the field line or perpendicular to the field line. So the uniform circular motion is going to happen, let's say that this is an XY plane, right? So this is X, this is Y. So the circular motion happens in the XY plane, but the Z direction is the direction of the magnetic field, And that's the direction in which our particle is going to drift. It's going to drift in this helical motion out of the screen, right? So let's go in and understand how this is going to happen. This velocity vector has two components. There's a component along the field line, and there's a component perpendicular to the field line. So this is a right angle. And we'll say that the velocity along the field line is the parallel part, and the velocity transverse or perpendicular is the transverse part. And our velocity vector is truly a vector that is just the combination of these two vectors. There is the transverse part, and there is the parallel part. This is just something you can always do. Sometimes it's useful, sometimes it's not necessarily useful, but in the case of this problem or this exploration of a physical phenomenon, it is useful to split a particular vector up into the transverse component and the parallel component. And so now let's see what we get. So we know that the magnetic force, which is a vector, is Q V cross B. But we just rewrote V, so let's put in our rewrite. There's the transverse component and the parallel component. These are vector cross product with B. The vector cross product is distributive. That is, crossing with B can distribute over the sum of these two vectors. But you have to keep the vector order in the same order, or else you introduce minus signs. So I'm going to write this as V transverse cross B plus V parallel cross B. Can you see that I kept the same order? The velocity vectors stayed on the left sides of the cross product. The magnetic field stayed on the right side of the cross product. So this is two terms. Vt cross B, and oops, I forgot the vector symbol, V parallel cross B with a Q. So this is the magnetic force on our little particle, our little positive charge Q right there. Okay, so why is this interesting? It's interesting because this term right here is 0. It's 0 because anytime you take the cross product between two vectors that are in the same direction, can you see that V parallel is parallel to B, right? That's just by definition what this component of the velocity is. So if it's parallel to B, then it's always going to go to 0, right? What's left over, though, is something over here that's not 0, the transverse part. So let's concentrate on this thing. Because by design, right, by definition, the transverse part is transverse to B, that means that the transverse part is at 90 degrees to B, to the magnetic field. So we can talk about the magnitude of the force, the magnetic force, and it's equal to Q, you take the magnitude, but it's the speed, but only the transverse component of the velocity, times the strength of the magnetic field. I'll just call it B, and I'll drop the vector symbol, right? So I'm talking about magnitudes. And this is a centripetal force. And so this transverse velocity is going to be the speed of the circular motion. Our little positive charge is going to circulate on the circle with V transverse. It's going to have a centripetal acceleration, which is V transverse squared divided by the radius, right? And the centripetal force is given by Q, V transverse B, right? So this describes the circular motion, but there is still an unaccelerated drift. of VP, right? Even though there is no force associated with VP, that doesn't mean that VP is zero, right? It just means that the drifting velocity does not change. It's unaccelerated because there's no force in that direction. And so you get genuinely this drift. So you get a drift of our particle with the parallel component, and you get circular motion along the sort of cycle of the helix of transverse, and the radius of this helix is related to other quantities, including the mass of our little particle, just by circular motion argument, right? Yeah, so this is the helix. I have a drift, and I have a transverse motion that is accelerated in uniform circular motion. This right here is a nice trick, right? And it's a trick that you can imagine using in lots of different contexts. You think of a particular vector relative to another vector in terms of a perpendicular part and a parallel part.